Okay, good. I speak on behalf of a lot of people. But we gathered some thoughts with Nicolas Pontieux and Guylaine Lagache, and this is a nice continuation of what Alexandre and Alessandro have shown, and it's about what can we do with dust interstellar emission, and I would like to plead for spectral studies, and so for that. So this is the abstract. I can move on. Here I would like to summarize what we know from these wonderful space missions and ground-based observatories. And so that was illustrated in that model by Compiègne et al. In 2011. And I would like to remind you that there was heroic effort by François Pajot in the 1980s. They went to the South Pole and they measured 1 point at 1 millimeter. That was the photometry we had got of the dust in the galactic center. And that was one photometric point. And now you can see the achievement that was done by Planck. And this is the map at all frequencies in a sort of animated film. And you can see that as we move along at high frequencies, the dust emission from our galaxy is dominant. This is the dominant emission, not stars. And the galactic plane is obvious in the middle in this all sky map. So what can we do with this map? So this has been thoroughly measured with many various methods. And here I just want to mention the workhorse method that has been used by Herschel and Planck, which is the modified blackbody, single temperature with one spectral index, emissivity index. And this is the whole sky map of emission from dust. At the end of the day, you get this emissivity index on the upper left and the temperature of dust. So basically, you see that at the center of a galaxy, it's a bit hotter. The gold belt is a bit colder, and then the diffuse emission has some fluctuation in temperature. And on the right, you see the what can be considered as the best effort as understanding the submillimetre emission. And this is a model by Guy et al. And I think all these missions are opening the way of measuring the dust emissivity in the millimeter domain and not only the submillimeter per se. And more efforts have been done by gaining higher angular resolution than Planck. And so this is one of such efforts made with NICA in 2 infrared dark clouds. And as you can see on the right, the fitting of this dust emission involves dust with an emissivity index that can be as large as 2.4. And so this is challenging for models. And there is another region which has been mapped like that. So NICA2 provides 1 and 2 millimeters simultaneously. So you can do spectral index directly. And you are not too much affected by a temperature indetermination because you are almost in the Rayleigh Jeans part. So this is another cloud that has been shown by Philippe André previously. And on the right plot, you can see that the emissivity index is varying. This is simply the ratio of the 2 bands, but this is directly linked to the emissivity index, and it varies up to 2.4 as well. So you can locate the positions where the index is large. So this kind of studies can be done also in the galactic plane and at the very center, so the central molecular zone. And here I've plotted a figure taken from Tang et al. And they did that with Aztec and Herschel combining Aztec and Herschel data. And you can see this, should I say, infamous anti-correlation of emissivity index and temperature on the upper right diagram. And again, the emissivity index can be as large as 2.4. This is quite difficult to explain with standard models in a quantitative way. Also, there are some temperature uncertainty if you assume an index at longer wavelengths, smaller wavelengths. So this is also something that will be addressed, that is addressed by NICA2. So the Gaston large program has a large sky, and Carl has shown already the map. Here I would like to show the map that was made by Xengeri with Laboca on Apex. And this is to show how we can gain from combining missions like Planck. And Planck will give very accurate brightness measurements on large angular scale. And you can combine them by adding the smaller details from Laboca in a consistent manner. And the map can show a lot of details which have to be understood. Things have been done also on nearby galaxies. I think it's the new frontier that we have to go through for the interstellar medium. We have to study the interstellar medium in nearby galaxies, so that we can resolve the details. And here is an example I take from Laboca measurements. And on the lower right figure, you can see the prediction from Herschel for this galaxy, NGC 1512. And in fact, Laboca measured a bit more and more extended. And so this is the famous submillimetre excess. So we hope to delve into that subject with NICA2. We have also a large program on nearby galaxies that has started with Susan Madden as PI. And so as a summary of my talk, if I run out of time, I've made a list of current issues in dust submillimeter emission. And what we see is that the spectrum in the millimeter is very rich, and it is not only occupied by dust emission, but there are many other features like CO lines. We know that in Planck, it makes the photometry difficult to interpret if we don't have the CO lines. We have also the free emission, the synchrotron emission, and we know that dust is complex. It has several components and probably several dust temperatures. So models and experiments make predictions, and we have to test them by making more accurate measurements. So in photometry, we have got the proper instruments, but I think it is clear that we need to go to the spectral dimension to get a new parameters on what we measure. And obviously, I think you have seen many talks now. The millimeter is dominated by the cosmic microwave background, and the anisotropies and polarization have to be measured. And the main foreground is dust emission. So we not only need to understand dust emission, but we need to measure it at a very high precision. And on the lower right part, you see a summary of what we know of a dust emissivity, dust emission. And you can see that there are still some uncertainties in the millimeter domain. And this is a log scale, so it hides the fact that we are still very poor in our understanding of millimeter emission. So we need for spectral studies, this is my main message, and we need also some decomposition of the dust spectrum, which is parsimonious, and we need to go beyond the single temperature, one emissivity dust model. And so there is work ongoing. And to show you the connection The PRISM mission, which was submitted but not accepted, it contained 32 bands, so narrow bands from 30 gigahertz to 6,000 gigahertz to tackle this problem of multi-component in the spectrum. Also, it's not too far now. People have been thinking of what the next space mission for ESA, and Voyage 2050 as a L mission with spectroscopic capabilities in the millimeter range. So this will also occupy the landscape soon. So I have one slide about Concerto. So Concerto, for the first time, has spectral capabilities in the millimeter domain. So we made a proposal to observe reference targets like the central molecular zone on the upper left, and also standard galaxies like NGC 253 or Centaurus A. And so the idea being just to measure the spectral index and to map the spectral index at different positions of a galaxy. This has never been done. And so we hope to also measure CO at the same time, so we can make a nice component separation on this. Then with organization in Grenoble about kids, we need some R&D to improve the spectral capabilities of kids. And so I have one slide on that, if it works. Yes, so the kit technology is really going fast around the world, and we need to keep an edge on our capabilities of bringing the instruments up to standards of astronomical observations. And so if we want to go to spectral capabilities, we need to go to no moving parts, contrary to Concerto, and maybe spectral capabilities close to the detectors. And why is that? Is that in that case, we can have a polarizer analysis separated from the instrument, and so we can have spectral polarization possibilities. And so with Alessandro is the motor in that. We are trying to test new ideas on making spectral capabilities. So we are talking low resolution, typically 100, not heterodyne resolution. The idea being to be able to separate all the components that are happening in the millimeter domain. And so I won't detail that, but so we are considering all these efforts. And so we are benefiting from money from Focus LabX, which I salute now. And so we have made also ERC proposals to further that research. Finally, I would like to finish on the need for a new 15-meter class telescope in the millimeter to do a survey type mission. And so these are the ideas that we have put forward, which would be a telescope like NOEMA class. And this is an optical study that was done by Samuel Leclerc and Andrea Catalano. And you can see that we can fit in a big cryostat a lot of kids. I will come back to that, and a half-wave plate. So we could have a millimeter polarizing instrument at high resolution. And so what would be the characteristic of this instrument? So it would be typically 20 arc-second resolution with a field of view of 1 square degree and 30,000 detectors. So we go another factor of 10 in Alessandro's ladder. And we could cover the millimeter domain from 1 to 3 millimeter. It would be polarization enabled. And a wide survey in a year could cover 6,000 square degree. And the idea being to beat cosmic variance for extragalactic studies, and also to have several galactic regions at this, in the same survey. We could go to deep surveys, so that would be more interesting for extragalactic studies. And the rough order of magnitude cost would be 15 million euros. But then we would need to accompany that for 10 years, so say 1 million a year, typically. So for PCMI, I think that the main target would be a complete millimeter census of the linked to the magnetic field. And we could also have, for the first time, spectral maps with a large covering. And so on that, it's not exactly quick, but it could be in this decade that we could see the happening of this antenna if it were accepted. And so you know, PCMI say which observatories for in the coming years. So I think there is a need for an all sky millimeter survey at high angular resolution, and we have the technology capabilities to do that in Europe. And so I will end up with that. Thank you very much.
Thank you. So there are questions from Marie-Vonne, Laurent, and Frédéric. And many other
Xavier, bonjour. Hello. This is also a question. I mean, when you say a CO, I think it's just the tip of the iceberg, and then you have, especially if you go in 1 millimeter in a region like the CMC, I'm sure that significant fraction of the flux at some places is in land because of these massive TMCs. Maybe several of them are on the line of sight, and each of them has a complex spectrum. Some of these spots have been known, they may already exist in line surveys of some of these spots. So I think it's not the best place to look for the data because the velocity structure is too complex, and maybe with the 100 resolution we can start to see something. If you look at the spectrum for such pictures, you say, oh, this was my, especially if you want to go to the millimeter, the spectrum will be even more complex at that point. So,
yeah, so yeah, I agree with you about more lines than that. I said CO because it's the most obvious, but obviously there are more components, and so yeah, the spectrum will be rich. But if we want to access the dust emission, we will need to deal with all these lines. They will be unresolved, so they will occupy, say, 1 bin of frequency or 2 bins, and that's it. So we'll have to deal with them, but Concerto allows simultaneous observations of these lines and the dust continuum, which is the main, you know, the most important thing here.
I was thinking that the region itself, the galactic center itself, is not the good place to go for the emissivity. Maybe other region will be.
Sure. Yeah. Yeah.
okay.
Yeah. So the famous Pause Nebula has been is also a target, and yes, then it's a question of ISO acceptance of proposals and us writing the proposals. So yep. Concerto is a great facility, so we will need to show what it can do.
Okay, Frédéric and Pierre.
Yeah, so just a short question about you say that basically you are in the reagents regime, but don't you really need the fine reduction for constrained dust emissivity if you have a limit of temperature and basically a limit of emissivity?
Yeah, so it's a good question. So if you want to constrain dust emissivity in the millimeter, I think already Rigby has shown that we can use Herschel as a thermometer. But we are not so much dependent on the exact temperature because we are mostly in the Rayleigh jeans. Now, if you are talking about measuring the emissivity in the far infrared, this is a big problem. And it's clear that a single black body is not enough, single gray body. That's not enough. So we need to have a way of measuring dust temperature along the line of sight. So I'm writing a paper on that. And the idea is that right now, we are assuming that the sun is the center of the universe. We are assuming that the temperature is the same along each line of sight. This is not right. We know that along one line of sight, the temperature is varying. So we are measuring a sort of average. So we should go beyond the single temperature. So to make the answer short, we need the peak of a far infrared emission to know the emissivity in the far infrared.
Thank you, Pierre.
Hello, François. So I have one comment. First comment is related to the dust problem. I think that you should not forget that there was a very large bandwidths receivers from recycling. Those are fantastic instruments to measure the properties of the dust along the large frequency ranges. 3 to 1 millimeter, and I think provides a lot of interesting constraints.
I think, yeah. Can you repeat the question, because
That's a
it's really tough.
I'm saying that currently with the very large bandwidths in NOEMA, this is a fantastic tool to measure over large frequency ranges the dust
Yes.
and continuum, and hence also to constrain the properties of the dust across cosmic time.
Right. Okay. Well, so for NOEMA and so on, it's a very high angular resolution measurements of very small clumps, and so this is important. And this is where I'm not an expert, but I know that heterodyne systems have got problems in measuring continuum over large bandwidth. So if we can show that it is possible with NOEMA, I would be glad to use this data, but this will be at very high angular resolution only. So it will not cover the diffuse medium.
So the question I have is regarding the new telescope. You didn't mention at all where you want to place it?
You are talking about the location of that telescope?
Yes.
Yes.
Where would you?
Yes. Okay. So this is this is left open right now, so that we don't discuss. I think it's best to be decided according to the scientific needs, and not to put that as a first prerequisite, if you want. So this is something we are doing in Grenoble, and I think this should be enlarged to the French community to say, what do we want with that telescope? Where can it be put so that it achieves the needs? So, going to Atacama or South Pole is very demanding. So, can we do something from Europe? I don't know. So this is left open. But I really think that we're in a position now to do an all sky survey at high angular resolution, which should be something really fantastic when we see how useful a Planck is, because we have the whole sky. I think the next step is to go to spectral dimension and to higher angular resolution over the whole sky.
1 millimeter or 2 millimeter?
So it would be 1 to 3 millimeters simultaneous.
You also, I mean, you only need one part of the sky.
I didn't get that. Sorry.
Only part of the sky, because it would be a northern or
yeah. Okay. Okay. Yeah.
Or you need 2 telescopes.
You need 2 telescopes, standard. Yeah.
Next to me.
But it's one antenna. I think Pierre mentioned he wanted 20 antennas, right?
Yes, yes, yes.
Right. So I just need 1 or 2. So it's a low-cost project. It's not 1 billion. Okay, we're talking maybe 20 million.
Okay, thank you.
Thank you.
Xavier.